So today our speaker is Professor Edward Jones. He's an associate professor and leader of the robotic learning lab at Imperial College London. He received his PhD from Imperial College and did a postdoc in University College London. He returned to Imperial College as a founding member of Dyson Robotics Lab. In 2017, he received the prestigious Royal Academy Award of Engineering Research Fellowship. His research lies in an intersection of robotics, computer vision, machine learning, with a particular focus on visually guided robotic manipulation. Today, he will talk about images, language, and ingredients of robotic learning. And we thank him for accepting the invitation. Professor, the stage is yours.
Thank you very much.
Thanks very much. Okay, so let me see if I can share my screen.
Yes, you can, I think.
Okay, let's try this. Okay, can you see?
Yes,
my
we can.
first slide?
Yeah.
Great. Okay, so let's start. So thank you very much for inviting me today. I'm going to talk about robot learning, really, from the perspective of images, language, and actions, which are really the three ingredients that you need in robot learning. Particularly these days, language is becoming much more common, and it's, the developments in large language models have allowed us to start introducing language into robot learning in a way that wasn't possible before. So I'm going to talk about these three different components of robot learning. Really, the work that I focus on is all about robot manipulation. So manipulation is the ability of a robot to physically interact with objects using their arms and hands. So this is quite different to other areas of robot learning, such as driverless cars or legged locomotion. The challenge really in manipulation is that you need very high precision for a lot of tasks, and also the tasks themselves are extremely diverse. So it's very, very difficult to teach robots all of these diverse tasks when each task itself often requires a lot of precision. So that's really the challenge that we're facing in this field. So let's start with a motivating example. So imagine you wanted to teach a robot how to hammer in a nail. And really what I mean by that is you would want the robot to be able to hammer in that nail wherever the nail is in the environment. So this is me in my lab moving around this nail, and the robot is hammering in wherever that nail is. Now, what we want to do that is we want to be able to teach the robot very efficiently. So we don't want to spend hours and hours and hours manually designing a controller for every single task. We would like the robot to learn this quickly. And really, what we've got to do is we've got to come up with a method to take in an observation of the world, or allow the robot to see the world through its camera observations, and then predict an action. So that action could be, for example, the velocity of the robot's gripper. Now, this big blue arrow here, that's the thing that we've got to design. We've got to come up with a way to get this arrow to predict the actions from the observation. This could be an end-to-end solution. So we could train one big neural network, for example, that could take in an observation and then directly predict actions at the output of that neural network. That's a very scalable solution in that it can just absorb more and more data. As we know with deep learning, usually the more data you give to a network, the better it becomes. So this is quite a scalable solution, but it does require an awful lot of data. So an alternative solution is a more modular pipeline, which would be much more data efficient. So that pipeline would include more traditional aspects of computer vision, such as object segmentation, object pose estimation, things like that. And then you would build up this reasoning pipeline by appending these modules together. And we explore different variations of both of these approaches in our work. So robot learning itself tries to get this robot to learn how to predict actions from the observations. And what we're going to do is we're going to provide the robot with a load of data. So here, let's say a load of different hammers and a load of different trajectories that those hammers take. We're going to do some machine learning, and then this will give us a controller. And the idea is that sometimes it's easier to design a learning algorithm and a way to collect data than to design the controller directly. And that's really the premise of machine learning. Instead of designing solutions manually, each time we have a new problem, if we've got the same learning algorithm that we can deploy across lots of different tasks, then maybe that's much easier to do. And because all we then need to provide is the data, we don't actually have to design the solutions manually ourselves. So let's take a look at the different types of robot learning. So you can think of the different types of robot learning as being the different types of machine learning that we're often taught about as undergraduates. So we're taught that there's supervised learning, and then there's unsupervised learning, and then there's reinforcement learning. And it's the same in robot learning, really. So I'm going to take you through these different types of robot learning in this talk. We're going to start off with reinforcement learning. Now, reinforcement learning is often when I tell people I work in robot learning, they assume that I work in reinforcement learning. But actually, that's not really quite how it is. Reinforcement learning hasn't really delivered on its promise. So let's say 5 years ago, everybody was very, very excited about reinforcement learning as that grand solution for robotics, but it hasn't really delivered. There's a lot of interesting work still going on, but it's taking a long time to get there. And this is one of the reasons why it's very, very difficult to get reinforcement learning working in the real world. When a robot learns a task with reinforcement learning, it has to fail at that task in order to then know that it shouldn't do that thing again. So in that example, it would get a reward that was quite low because it didn't succeed. But each time the robot fails, the human has to reset the environment. And that's me in the lab there resetting the environment. I don't really want to be spending my life resetting environments to enable a robot to learn a task. And so for that reason, reinforcement learning hasn't really delivered on its promise. There's still a lot of work in the sim to real gap. So if we can train robots in simulation, then of course we don't need to manually do this resetting. And if we can narrow down that sim to real gap, then maybe we can just deploy simulation trained robots in the real world. But it's still quite difficult to design reward functions across a large, diverse set of tasks, which is the case in robot manipulation. In something like legged locomotion, the reward function is often much simpler, and it's a very similar reward function across different tasks. Just keep moving forwards and don't fall over. But with manipulation, all of the tasks are very different. So it's still very difficult to get all of those reward functions designed. So I don't really work that much on reinforcement learning. I work mainly on supervised learning and unsupervised learning. So let's have a look at what supervised learning looks like in robot learning. The most simple form of supervised learning in robot learning would be something like behavioral cloning. So this is where the human would be effectively providing the labels for the data, and they would do that by moving the robot physically. So here we've got somebody moving a robot arm in order to show the robot how to hammer in a nail. And the human would do that over lots of different viewpoints from the robot's perspective so that it can see the hammer from different viewpoints. And in this example, we've got a camera mounted to the robot's wrist, which enables the robot to then observe that nail from all the different perspectives it requires. In the real world, this is what this looks like. So this is me in my lab. And now I'm teaching the robot. The robot isn't exploring autonomously like with reinforcement learning, but I've still got to effectively keep resetting the environment and provide lots and lots of demonstrations. So it's still quite laborious. It's a little bit less laborious than reinforcement learning, but you still typically, with behavioral cloning, you have to provide a lot of demonstrations. You would probably have to provide over 100 demonstrations for this task. So what we've been thinking about is different inductive biases that we can introduce to make this much more efficient. And here's one of them. So the specific trajectory as the robot approaches the nail is actually not that important. And really that can just be a straight line. What's really important is this pink trajectory, which is the interaction between the hammer and the nail. And really that's the bit that we actually need to provide for the robot. And maybe the rest of it, the robot can learn in a self-supervised manner. So what we do is we define something called the bottleneck pose, which is the pose of the gripper just before it physically interacts with the objects. That's the bit that the robot really needs to reach, and then it can just replay the human demonstration. And everything else, actually, the robot can collect that data autonomously by itself. We don't need to be physically moving the robot around in this blue area. The robot can actually collect that data by itself. So what we're going to do is we're going to train a robot to take in a live image and use supervised learning to predict the robot's velocity, okay? And to collect that data, we're going to do it in a self-supervised manner. So this is what it looks like if we want to teach a robot to hammer and nail using this coarse-refined imitation learning framework. First of all, the human will provide a single demonstration of the task. And that's all the human needs to do for this task. The human can then step away. It's just 5 seconds of interaction time between the human and the robot, and the rest of it is fully autonomous. The robot will then move around the object with a camera mounted to the wrist and collect a data set of image and action pairs. And these image action pairs tell the robot where it needs to move for each image in order to reach the nail. And then we collect a second data set, this time much closer to the object. So this is a last inch correction network, which collects similar images and actions to in stage 2, but this time right up close to that object. And now we've got these two self-supervised data sets telling the robot what actions to predict for each image. And once we train those networks, we can then deploy the robot with the nail in a new configuration as follows. First of all, the robot will move towards the nail using that first neural network that we trained. Then the robot will make one final last inch correction using that second neural network we trained. And finally, the robot will simply replay the human demonstration. So all of this is possible with only about 5 seconds of human interaction time, and the rest of the time is fully self-supervised. And then we can deploy that same algorithm across a range of different tasks. So each of these tasks here, for each of these, we've shown a single human demonstration for about 5 seconds of human time. And then the robot is able to go around and perform this task, even with those objects in novel configurations. So we've got this one algorithm, and all we need to do is provide a single demonstration, and the robot can then learn that task autonomously. We don't need to change that algorithm at all for each individual task. So it's a very general method, and we're able to use it across diverse, everyday real-world tasks like these. Let's look at some of the limitations of this method, though. So one of the limitations is self-occlusion. And this is because what we're doing is we're mounting a camera to the robot's wrist. So if you look at the image on the left, quite a lot of that image is occluded because the camera is just mounted above that hammer. Now, in this particular task, that's okay because you can still see a bit of the orange nail block beneath it. But in general, this might be much more problematic. So this is one of the problems. And a solution is to use a head camera rather than a wrist camera. So a head camera gives the robot a different perspective, and it won't be self-occluded by whatever the robot is grasping. However, it's not very good for spatial generalization. So with a wrist-mounted camera, you can generalize a controller across the table, for example, here, without having to retrain the robot in different configurations, because the image is conditioned on only the relative pose between the object and the gripper, not the global pose of the object. Whereas when you have a head cam, the image is conditioned on the global pose of the object. So wherever the object is globally, that image is going to be different. So it does solve the self-occlusion problem, but it also introduces another problem that we then have to solve. Another limitation of this approach is that we have slow data collection. So we still need, even though the human doesn't have to collect this blue trajectory ourselves, it still takes about 15 or 20 minutes to collect this data. So ideally, we would want to avoid that. And it would be nice if the robot didn't have to collect this data at all. So what we started thinking about is, how can we do this with a head camera without having to collect that data? And we developed a method based on the concept of trajectory transfer. So let's say you have a task here where the robot is scooping up an egg, and we've got this trajectory shown in the green line here. What we want to do is transfer that trajectory to another point in the environment where the object, the pan here, has moved across the table. Now, the appearance of the pan is very different here because it's moved physically across the table, and therefore when you have a fixed head camera, you're gonna have a different image of that object. So what we want to do is transfer the trajectory from the demonstration over to the deployment. So we approach this from the perspective of unseen object pose estimation. And I'll explain what that means by showing you the pipeline that we implemented. So first of all, we have an RGBD image and a trajectory, and that's our observation. So those are the things that the robot is showing during the demonstration. And again, it's just a single demonstration of a task. And then during deployment, when the robot wants to actually now interact with the object autonomously, the object has moved to another place. So the mug now has moved to a different pose on the table. And now the robot has to figure out what the end effector trajectory should be in order to interact with the object. And we can solve this by using unseen object pose estimation. So unseen object pose estimation is where we are doing pose estimation between two images of the same object, but there hasn't been any explicit training on those objects. So that's different to normal object pose estimation, where you would be training explicitly on lots of different views of a particular object, or maybe lots of different views and lots of different shapes across a class of objects. In this scenario, we don't have that pre-training because we don't know what this object is going to be. We don't want to have to know in advance that the robot is going to interact with a cup and then train on lots of cups, because that then overfits to a particular type of object. So once you've done this unseen object pose estimation, there's a mathematical formulation for how you can use that to then transfer the trajectory from the demonstration scene to the deployment scene. And then we have this aligned trajectory, which allows the robot to interact with the object. Let's see what this looks like in the real world. Okay, so this is one of my students here teaching a robot how to place a toy piece of bread in a toaster. So he's providing this single demonstration. And that's all that we need to provide for the robot. And as you can see here, the robot is now going to deploy that skill immediately afterwards. There's no actual training here, and it's not collecting any further data collection. The robot is now able to insert the bread in the toaster, even though the toaster is in a different configuration. And we've introduced all of these distractor objects and changed the color of the tablecloth. And also we're now changing the height of the toaster. So the toaster is moving up here, and we're really showing 6 degrees of freedom generalization spatially. So we're able to achieve all of this with just a single demonstration now, and the robot can be deployed immediately after the demonstration without having to wait around and collect all of that data. And we can deploy that same method across lots of different tasks. So here we have a range of everyday tasks. Each of these uses that same method. We're using trajectory transfer and unseen object pose estimation in order to enable the robot to generalize from the demonstration scene to the testing scene. And this is a video that one of my students recorded just a few days ago on chaining together different tasks. So if we trained all of these different subtasks, we can chain them together to perform a long horizon task. And here we've got an example of the robot simulating making breakfast. So inserting bread in the toaster, getting a tea bag out, pouring water into the tea bag, placing the toast onto the cup, onto the plate there. And of course, we're not simply telling the robot where these objects are. The robot is inferring them using computer vision from that camera mounted to its head. And all of this would have taken just, well, it's sort of a few seconds per task. So you could have taught the robot all of these tasks with a minute or two of interaction, and then the robot has learned this quite complex multi-stage long horizon task. All right, so at the moment what we're really talking about is generalization to novel configurations of objects. So if the objects move around in an environment, then the robot will be able to interact with those objects wherever they are. We haven't really done any generalization to novel object shapes, okay? And this is what I'm going to talk about now. So let's say we want to train a robot to pour into a mug from a teapot, from a teapot, yeah. but we want this to then generalize to novel shapes of mugs and teapots. So our training data might look like the data at the top here, where we've got different teapots and different mugs, and then the testing data might be the mugs and teapots at the bottom. And really what this looks like when we deploy this is we're going to provide a few demonstrations of pouring something, simulating pouring liquid into a mug. So there's a few demonstrations here that my student was providing. And now the robot is able to immediately generalize and perform this task across a wide range of different shapes of those objects. So here, not only is the teapot shape a novel shape that wasn't seen during the demonstrations, but also the mug itself is a novel shape as well. So how do we do this? I'm going to take you through this big neural network that we train. Okay. At the input to the neural network, we're going to take a representation of a number of demonstrations and also a candidate alignment of objects for the test objects. Okay. Now, what we're using here are point clouds, and we're going to take all of these, the demonstrations plus the candidate test alignment, and create a local embedding of these point clouds. And then what we're going to do is we're going to create a big graph from all of these local embeddings. And we have this big graph that now connects together all of the different local components of the demonstrations, but also the local components of the test alignment. And then what we're going to do is from this graph, we're going to predict an energy. And then during deployment, we're going to minimize this energy. And the minimum energy will then be the optimal test alignment. So we're going to change the test alignment. We're going to keep the demonstration alignment fixed because we've already given those 3 or 4 demonstrations. And the thing that we're going to change and optimize for is that test alignment by minimizing the energy. And then when we have a minimum energy, hopefully that will be a very good test alignment. Now, the nice thing about this is it's in context learning in that all we're doing is providing the demonstration examples at the input. We're not actually explicitly changing or training the neural network on that data. So it's a little bit like in context learning with something like ChatGPT, where you just provide a few examples and then the neural network conditions on those examples and outputs its predictions. But how do we get all of this training data? Because it's very difficult to get lots of training data in robotics. We found that actually we're able to do this simply by randomly warping objects in simulation to generate virtual demonstrations. So we're going to preserve the semantic alignment of objects by simply choosing 2 random points on the objects. Here, we got a random objects. We've got an airplane and a motorbike, just 2 arbitrary objects. Then we're going to fix a couple of points of those objects relative to each other and randomly warp the objects and generate different diverse training data. And then we're going to do that across lots of different objects. And we found that actually this is sufficient to give us a prior on how objects should be aligned given a few demonstrations of a task. And then here's some results across a range of different tasks. So we're using the same method across all of these tasks. Here's my student Vitalis showing some demonstrations of these tasks. And then once those demonstrations have been provided, the robot then can solve the task, even though the objects it's been shown are novel objects that it's never seen before. And we're able to do this immediately after the demonstrations. So the robot doesn't have to do any learning once it's seen the demonstrations. It simply conditions that big neural network on those demonstrations and does in-context learning. Okay. So that's supervised learning, really. So even though there is some element of unsupervised learning, let's say, really, we're still providing human demonstrations of tasks. So there is still this requirement for a human to come in and show the robot how to interact with objects. It would be nice if we could do this without having to provide demonstrations and just do it all with unsupervised learning. And really what I mean here is self-supervised learning. So essentially, can we make use of data that's easily accessible, readily available, that we don't have to manually annotate? And the motivation for this, or the reason why this might be possible, is because this is really how all the big breakthroughs in AI over the last 2 or 3 years came about. So So back in the early days of deep learning, it was all about supervised learning and ImageNet and manually labeling images. The big breakthroughs, things like image diffusion models and ChatGPT, have largely come about through unsupervised learning and training on these huge data sets of images and text that's just freely available, and we don't have to go in and label that data. So let's talk about 3 types of data. So remember, my talk is about images, language, and actions. We haven't really talked about language yet. We've talked about images and actions a lot because the robot has to take in an image and predict an action. I'm going to now start introducing language. And language enables us to do things, to very interesting things with robots that we can only really do with language. So the problem with action data is there's very little available data out there. So we don't really have big data sets of robot actions out there freely available. There are some initiatives to scale up robot data, but it's much, much smaller than the amount of image and language data that we have that's just effectively freely available for people to use and train on. So really, we want to capitalize on the image and language data. So what are some things that we can do with image and language data when we scale up data collection? Well, one thing is that we can predict an image from language, okay? And this is what image diffusion models do. So things like OpenAI's DALL-E, Stable Diffusion, they take in a language command and predict an image. And when DALL-E 2 arrived last summer, and it became publicly available for us to use, we started thinking about ways in which we might be able to use this in robotics. So image diffusion models take in a text description and create an image. And these images are very, very realistic. And we started thinking about, well, maybe there's a way we can use this and exploit it for robotics. And we came up with this idea called DALL-E bot. A DALL-E bot is a method where we will take in an initial scene. So here, for example, we have a plate, a knife, a fork, and a spoon. And the robot then takes a look at that scene, comes up with a textual description of that scene. So we have in the middle here a fork, a knife, a plate, and a spoon. And we will generate an image of that scene. And the idea is that when the robot generates an image with this text description, it's going to create the most natural looking image that it can think of. And so in this example, it's going to put the knife to the right of the plate, the fork to the left of the plate, and the spoon above the plate. And that's because the majority of images containing plates, knives, forks, and spoons have this kind of arrangement. It's the sort of the default way to set a table if you were to sort of average all the ways people do this. And so we're using this web scale image prior to enable the robot to figure out where objects should be placed relative to each other without us having to manually tell the robot that knives should go to the right of plates and forks should go to the left of plates, etc. Here's the actual pipeline. So starting from the top left, the robot takes in an observation of the scene and then detects the objects and creates masks. And then for each of those masks, it uses GPT to a visual language model to caption that and extract the noun, so the name of the object. And then we generate a prompt here. So this prompt is a fork, a knife, a plate, and a spoon top down. The top down bit is a little bit of prompt engineering we introduce in order to create an image that appears as if the robot is viewing it from above, directly above the table. Then with this text description, we generate the image. And then from that image, we detect the objects and try to match them back to those real world objects in the real scene, so that there's a one-to-one mapping between the generated objects and the real objects. And then finally, in the bottom left, the robot will then move the object around such that it recreates this image that it generated using DALL-E. One of the things we have to do, though, is to filter out the images, because some of the images are just not appropriate. They might have the wrong number of objects. Or they might not generate objects where there's a one-to-one mapping between the generated image and the real objects. So we do have to do a little bit of filtering, but this is fine because these methods are stochastic and they generate lots and lots of diverse images, and we can just generate a few and choose the best one which matches the objects in the real scene. So that's what we do here. And then finally, I'm going to show you now what this looks like in the real world. So we place these objects randomly in front of the robot. The robot then generates the goal image, which you can see in the top right, and then it recreates that goal image by moving the objects around in front of it. And here you can see that the robot moves the plate away from the center of the table, and that's just a little bit of task planning that we introduce in order to avoid collisions when the robot is moving objects around on the table. So all of this is possible without us having to manually tell the robot that this is how we should be laying tables. Let's look at some more results. Here we have an office scene. So the robot here is able to figure out that the keyboard should be aligned nicely parallel to the bottom edge of the monitor, and that the mouse and the mug should be arranged sort of to the side or just below the keyboard. And finally, we have a fruit scene. So here we have a robot realizing that the apples and the orange should go inside basket. Now, this task, you might think, well, this is pretty easy. It's just a container, and you just tell the robot to put things in the container. But remember that this is unsupervised, and that we didn't have to tell the robot that apples and oranges should go inside fruit baskets. It just figures that out because it's seen lots of images of fruit baskets with apples and oranges in them on the internet. So even though for each particular task, it might be fairly easy to script some kind of rule as to how objects should be arranged, we don't want to have to do that, because then we'd have to do that for every single possible scene that the robot will face. Okay, let's think of some of the limitations, though, of DALL-E Bot. One of the limitations is that the generated objects might be different to the real objects. So all we're providing is a text description of the object, like knife or plate. We're not actually showing the robot the real objects. So the generated objects might be different, and therefore it might be difficult to match them back to those real objects later on. Another limitation is that we can only generate 2D images. So these image diffusion models are trained on 2D images, and therefore they are going to predict 2D images. But the real world is, of course, 3D. So what if we want to do something where you want to, for example, stack something on a shelf? That wouldn't be so easy with a 2D image. And thirdly, the robot can't follow a language command. So what we're really doing here with DALL-E Bot is saying that the robot is just going to rearrange objects in a way that conforms to the natural way that these objects should appear according to images that it's seen downloaded from the internet. But you might want to give some extra commands. So you might want to tell the robot, oh, actually put the knife inside the bowl, something like that. That might be something you want the robot to do. So you might want to actually provide a text command for a language command for the task. So we have some solutions to these. Solution to problem one is that we're actually going to move the real objects around in imagination. So rather than just generating an arbitrary object using a language description, we're going to take that real object and move that object around in imagination. To solve the issue with only generating 2D images, we're going to do this in 3D space. So we're going to create a 3D nerf of the scene, 3D reconstruction of the scene, and then take the real images, the real objects, and move them around within this 3D environment. And finally, the third challenge is we can't follow a language command. This time, we're actually going to now take in a language command and compute the clit similarity between the language command and the image of the object in a novel pose. So I'll show you what that looks like in a minute. But really what we're doing here that's different to what we're doing with DALL-E Bot is with DALL-E Bot, we took in language and predicted an image. Now what we're doing is we are taking in language and comparing the embedding of that language using clip to the embedding of an image. And that image is a candidate hypothesis as to where maybe it's a good place to put an object. And we're going to render an image of that object in that place and then see how similar that is to the language embedding of the language command. Okay, this led to this method that we designed called Dream to Real. And it looks a little bit like this. So on the left-hand side, we have the robot and a scene. So in that scene, we have some shelves and some bottles. And the human command is, let's say, 3 bottles aligned in a row. So we want the robot to create this scene where there are 3 bottles aligned in a row. First of all, the robot builds up a nerf of the scene. So it will scan the scene and then build up a nerf. And then the robot will render imagined scenes using this nerf. So that's what's in the third image here, where you've got this heat map and the purple and blue lines. Those are all candidate poses of the strawberry bottle. And we're rendering images of the bottle in those poses and then computing the similarity to the text command. And then we're choosing the pose with the highest similarity and then moving the object there physically. So this is what it looks like for this task. You can see the heat map in the top right, which and the higher kind of the heat map on the top shelf showing the sort of yellowy scores. That's where there's a higher similarity to the heat map on the bottom where you've got the purpley scores. So the robot here is able to figure out that it needs to place the object next to the 2 bottles because we've told it to align the bottles in a row. Here's another example. So here the command is put the apple inside the blue and white bowl. Okay, so the robot is going to scan the scene and then imagine the apple in lots of different poses. And the score for all those different poses is again shown in the heat map in the top right. And then the robot finds the best pose according to the similarity between the rendered image and the text command. And finally here, we can also create shapes here. So we have some pool balls on a table and we want the robot to create an X shape. So the robot imagines the balls in lots of different poses. And then when it renders an image of the one where the balls are all in an X shape, that has very high similarity to the language command. Okay, so I'm just going to talk about one final project we've been working on. So in the dream to real method, we compared the embedding between the language command and a rendered image of a hypothesis. What about actually predicting actions? So in the methods that I've shown you just now, DALL-E bot and dream to real, we're really just doing object rearrangement. So we're generating an image somehow of what we think the final arrangement should be. But what about more complex tasks where it's not just about coming up with a goal image and maybe the actual trajectory itself of the robot is a little bit more complex? Can we directly predict actions from image and language? And really what we did in this project is we wanted to see what we can do with just using GPT-4 in order to predict directly dense trajectories of robot arms solving tasks. So here's an example. Let's say the task is wipe the plate with the sponge. What we want GPT to do is to figure out how to predict this sequence of poses for the end effector to move through in order to wipe the plate with the sponge. So what we're doing is we're studying the internal abilities of GPT in order to assess how good it is at really solving more complex robotics tasks, and really studying the internal knowledge about robotics that GPT has. So here's the pipeline. So if we look on the left, we're going to have an initial prompt, which is the task, the description of the task. So for example, shake the mustard bottle. Then at the bottom left, we've got this task agnostic prompt. So we have one big prompt that we're going to use in order to explain to GPT or give it guidance as to how it should be solving these tasks, but it's in a task agnostic manner. So we're not telling it how to shake the mustard bottle. We're just telling it things like, think internally about the trajectories that the robot should follow, consider collisions with other objects, all of these task agnostic hints and guidances that GPT can find useful in order to then predict the task specific trajectory. So in the bottom middle here, we have language-based planning. So the robot is going to have an internal monologue by generating its own thought process. And then through this, it will generate some code, which we will then run on the robot. So this is what this looks like when we execute this on a range of different tasks. So for each of these tasks, it's the same task agnostic prompt that doesn't know anything about these specific tasks. And we simply then append to the prompt the text description of the task that we want the robot to solve. So these are all tasks which involve some kind of reasoning about either kind of more complex trajectories or quite complex spatial reasoning with respect to different objects. And we're able to do this over a range of different tasks. Here are the results, the success rates. So the success rates are certainly nowhere near 100% on average, but this was the first work to really explore what does GPT really know about these low-level control and dense predictions of trajectories. So we're getting over, on average, a 50% success rate of all of these different tasks. And this is really promising because we didn't necessarily expect GPT to be good enough to do these tasks, because often the assumption is because GPT hasn't been trained on physical action data, then it probably won't really work for low-level control. But actually, we found that for many tasks, it does work quite well. And we also found that GPT is able to reason about failure cases and then adapt its reasoning accordingly. So in this example, the task is to pick up the bowl. Now the robot moves down and it's seeing, by the way, it's seeing a segmentation of the object. That's how the robot knows where the objects are. It has a mask, a segmentation mask of the objects. The robot fails the first time, then it tries to grasp the bowl in a slightly different way. Again, it realizes that it failed, and it realizes it failed because when it picked the bowl up, the bowl didn't move, or it tried to pick it up, it didn't move. And then the robot attempts that again. So let's look at that video again. So the robot task is pick up the bowl. The robot sees the bowl with a segmentation mask, and it realizes that it's failed to pick it up. So it then has another go. It tries to pick up the bowl along the side. And then it realizes that it's failed that again. So then it tries to pick up the bowl along a different side with the gripper orientated at a different angle. So it clearly has this understanding that in order to solve the task when it's failed a couple of times, it needs to diversify its possible solutions and try out a few different options. Okay, well, that's the end of my talk. Thank you very much for listening. I just wanted to say thank you to my team. So these are my students who have been working with me on all of these projects. I'd like to fund my sponsors, so EPSRC, Dyson, and the Royal Academy of Engineering. And I'd love to take any questions if there are any.
Yes. Thanks a lot, Edward. Thank you very much for this very interesting talk. So let's start with the questions. Any here?
Actually, I have.
Yes. Okay, go on.
Hello, Professor. Actually, I have a question. I don't know how relevant is it, but I'm going to ask anyway. Think of a factory automation scenario that we have lots of robots, actually not one, and we want to train them on real time, all of them at real time. And is it possible kind of online information sharing between these robots to make to facilitate the learning process, maybe?
Well, certainly, I mean, in general, if you have a load of robots collecting data and you want to share that data, then you can certainly do that. I guess if these robots are learning autonomously using something like reinforcement learning, then you'd have to be careful about data distributions and things like on-policy learning and off-policy learning. But certainly it's possible to combine data sets from different robots in real time. And there's been lots of work on that. I think Google did some work on this a few years ago on having multiple robots learning together and sharing that data in an asynchronous manner. I think for the work that we're doing in my lab, the equivalent would be something like imitation learning, where robots are trying to solve tasks, and then maybe there's a single human going around showing the robots how to perform those tasks and providing demonstrations where necessary. And let's say there's a robot trying to solve a particular task and it doesn't know how to do it, so it requests help from a human. The human could then go over to that robot, provide a demonstration to that robot, and then that one demonstration data could then be shared across all of the different robots. So they would all benefit from that one demonstration.
Thank you. Thank you for your time.
Any other questions?
I have a question. Actually, how many actions are there for imitation learning, and how many demonstrations were there? And for the second and the third project, did you use the demonstrations from the first project that you had, and the actions that you were taking, kind of continuous action demonstrations from the first task?
Okay, so I think your first question was how many demonstrations do we need? So for, let's say that if you're looking at this, the videos now, the task in the top right is hammering in the nail. Task like that, where it's just a single task, you only need a single demonstration. We're able to get generalization across the task space, so generalization to the poses of the object just from a single demonstration. If you look at the video in the bottom, with the green tablecloth where the robot is pouring from a kettle, a teapot into a mug, that task required 4 demonstrations across different teapots and mugs. So we have 4 different teapots, 4 different mugs, we have demonstrations across those, and then we're able to generalize to all of these novel instances of the objects. I think your second question was about the projects where we're doing it in a more unsupervised manner, and we're generating images and rendering images and bringing in language. How does the robot actually know how to physically interact with those objects? Well,
With actually different novel objects and generalizing to different novel objects, how does it work with just few demonstrations and few objects to generalize to other objects?
so with the, for example, with the video on the top where the robot is setting the table, we just have a very, very simple primitive for how the robot can pick up those objects. And this robot is actually has a suction gripper on it. And simply we just say to the robot, go to the middle of the object, apply suction, and then lift the object up. So, and it's the same for the video at the bottom with the robot picking up the bottle and placing it on the shelf. The robot doesn't have to really have very complex understanding of how to physically interact with the object. It's simply applying suction to the object and then moving the object around. So those tasks are more about figuring out where an object should be in the environment, not about complex interaction with the objects. The final project I talked about where we were studying, can GPT actually predict trajectories? That didn't have any demonstrations either, because the whole point of that project was to see, can GPT itself, using its own internal knowledge of robotics, predict trajectories through which the robot should move in order to solve a task. So we weren't actually using any imitation learning for the later projects at all. We were more studying how can this stuff be done in an unsupervised manner without us having to go in and provide those demonstrations.
Thank you for that. Another question of mine is, how can we have, for example, a more robust policy with a few demonstrations and, for example, using reinforcement learning, but without having the computer vision or NLP as a state space? Because when you use vision or NLP as a state space, and I'm talking about more computer vision, you have too much priors, and it sees from a camera, it's have too much priors, and it's more of the full observable environment. With partial observable environment, how can we limit our state space and action space, and can we have a more robust and control and policy for tasks without using too much complex state space and action space?
So, I mean, yeah, I think are you really asking about how can you, let's say, reduce the dimensionality of the learning space? Yeah. So that's a big part of robot learning, because we really want to be performing our learning over the minimum dimension space so that we get the best regularization and generalization. However, if we reduce the dimensionality too far, then there's not sufficient information for the robot to actually solve the task. So for example, let's look at the video on the left, scooping the egg. If we reduce the state space down such that it was just a single pixel in the image showing where the pan is, that isn't sufficient, because then you don't know the orientation of the pan. So there's a few ways that you can do this. One is you can represent object poses you can sort of go from use a computer vision front end to your pipeline that will then reduce the dimensionality from image space down to pose space. And then you might be able to represent objects in terms of a 6 degrees of freedom pose. So 3 translation components and 3 orientation components. That works reasonably well if you're interacting with the same object during testing that you trained on. But if you then want to generalize to novel objects, it doesn't work so well, because the objects have different shapes, and therefore the pose of one object doesn't necessarily align with the pose of another object, because the shapes are going to be different. So that's when it becomes really hard, and coming up with representations that are meaningful but also low dimensional. In the project and with the green tablecloth along the bottom, where we're showing generalization to novel objects, the way we did this is we trained a big graph neural network to take in point clouds and essentially just reduce the dimensionality as we go through the neural network to get to a space that's reasonably low dimensional, which then allows us to do some inference, which is quite typical in deep learning. You would start with high dimensional data, reduce the dimensionality down. But in that project, because the objects have various different shapes, we don't reduce it so far down that it's just poses of objects, because that would capture the shape of those individual objects. So it's still higher dimensional than just 6 degrees of freedom poses. And it's somewhere in between 6 degrees of freedom and the full original dimensionality of the observation space.
Thank you for the response.
Emrecan, maybe you can unmute yourself and ask your question.
Okay, thank you. So first of all, that was a great talk. Thank you for that. So my question is more about this architectural design of this policy stuff. So in the DALL-E bot, you conditioned on the initial image and the final image, and you somehow generate this by using a diffusion-based approach. But for training from scratch in an imitation learning approach, we need some perceptual encoder, right? For example, for vision, for action, and also to produce action to tell the end effector where to go. We need an action decoder. So I'm interested in your model design and architectures. And so how do you handle these in your projects? Is there a specific controller like in Palmi, or so? Yeah.
Sure.
Or you train them from scratch?
Yeah, so we're doing things quite differently to how imitation learning is normally done. So a traditional behavioral cloning type approach, which is just kind of regular supervised learning on image action pairs. The typical approach would be to train a robot in an end-to-end manner, where you would directly predict from image to action, and you might use something like a transformer, let's say, in order to do that. However, that's still very, very inefficient, and it requires lots and lots of demonstrations. So a lot of our work is thinking about how can we do this much more efficiently. And there's a couple of things that we do in our imitation learning work. One is that we, in order to get to, one of the sort of inductive biases is we say, we can treat object manipulation as a pose estimation problem, where we try to predict the pose at where the object is and then move the gripper to that object pose. That means that it really becomes a pose estimation problem. And a lot of our work is about saying, well, where is the object in the environment? And then once I know where it is, the robot can then move to that pose, as opposed to an end-to-end neural network, which has to make predictions at every frame that the robot sees. It has to make a a prediction about the instantaneous action the robot should be taking. Once you approach it from the pose estimation perspective, then it becomes more efficient because the object, as long as the object doesn't move, then the robot just has to move to the object's pose. It doesn't have to predict complex trajectories. And so by reducing the search space of the robot just to a pose estimation problem, that's one way we get this efficiency. The other is that for the actual interaction with the object, what we say is once the robot is aligned appropriately with the object, it can just replay that demonstration, and the action part isn't actually being predicted at all. It is simply remembering what the human did. So in the example on the left, where we've got the robot scooping up the egg, there's quite a complex trajectory there, getting that spatula underneath the egg and lifting it up. If you were to train this through regular behavioral cloning with something like a transformer, you might need hundreds of demonstrations in order to get this behavior. Whereas if you just focus on the alignment part and then you replay the demonstration, this is much more efficient. So we're doing things quite differently to how, let's say, Google are doing their behavioral cloning work. And this enables us to teach robots very, very quickly without requiring hundreds of demonstrations for each task.
Oh, I see. So that's a great answer. Thank you. So just a quick follow-up. So one thing I am facing about regarding this transformer stuff is, so these robot tasks have, I think, two different parts. One is achieving the object. So the second part is completing the task, right? For example, catching the block and rotating to the right. So the hardest part is for my side while training is achieving the object. So I think we are performing a curriculum learning approach for that, right, in an unsupervised way. So yeah, so how do you handle this? So you split these tasks in two parts, as you mentioned in the talk, at the beginning of the talk. So
yeah, I suppose maybe there's three types of reasoning that's going on. One is what task should the robot execute? The second is where is the object in the environment? And the third is how should the robot interact with the object once it reaches the object? So these are three different types of reasoning. And we're breaking the reasoning down into these three modes, as opposed to just training one big network on everything. So if you train one big network on everything, it's quite scalable in that it can just absorb data, but it's very, very inefficient, and you can't just teach a new robot a new task in just a few seconds. The way I see, so that the imitation learning work we're really doing is breaking down into where is the object and then how to interact with it. But we're not then studying how does a robot know which task to perform. So with the scooping the egg task on the left, we're simply telling the robot, okay, now do the task which is scooping the egg. The robot isn't deciding that that's the task it needs to do next. Whereas the project at the top with the knife and fork and the spoon and the plate, that's more about the robot deciding which task it needs to execute next. So it's deciding, I need to pick up a spoon, I need to pick up a plate, I need to put the knife down. And it's really using this web scale prior of what images look like in the natural world to decide which object to place where.
And you use also language models for that, so training step by step. I see. Thank you for the detailed answer.
You're welcome.
We are already a bit over time. Sorry about that. And thanks a lot, everyone, for your. There is one more question. I mean, do you wanna, or we can end it if you don't have time? It's fine.
I can take another question. Yeah, that's fine.
Go ahead then. Just unmute yourself and.
It's very quick. I just wanted to say that I find the example on the top right corner particularly amusing because before hitting the nail, it sort of lifts up the hammer, which is a very human thing to do compared to the other approaches that the robot performs. And that's probably because whoever taught it to do it did it like that, right?
Yeah. So that's me actually teaching the robot.
Yeah.
Right.
So
yeah, I mean, I think I could have done that without lifting the hammer up and just gone straight into the nail. It probably would have worked, but it kind of looks more natural doing it this way. So it's sort of give an example that you can provide this complex trajectory and the robot can just replay it.
Exactly. And what I want to ask about that is, do you think you could implement an optimization strategy where it gets rid of some of the human things that it does to perform the task more efficiently without, wasting energy. Because some of the things that we do as humans are due to our incompetence compared to robots, like our strength. It could learn from a human and then optimize it, maybe. Do you think that's possible?
Yeah, so certainly a lot of work going on in other labs on learning from suboptimal demonstrations or sort of superhuman performance going beyond the demonstrations. We're not really working that in my lab. I think the issue is it's very difficult for a robot to know just by observing a demonstration which parts of the demonstration are important and which parts aren't important. So here, where the robot is lifting the hammer up and banging it down on the nail, how does the robot know that it shouldn't lift the hammer up? It would then have to try out this task in lots of different configurations and get some feedback from the human, perhaps. And that then is essentially reinforcement learning, which then leads to all of the issues that I spoke about at the beginning. If you want this to be done in an unsupervised manner where the robot simply takes the demonstration and then adapts that data according to what it thinks is an optimal solution, there's a risk that the robot would then end up assuming things about the task that are not actually what the human wanted the robot to do. So, for example, you could add in smoothness to make the trajectory very smooth, but then maybe actually you needed this very complicated, wiggly, jerky motion because that's just what the task requires. So I'm kind of, with my work, assuming that the robot is able to provide a good demonstration, and the thing that the human provides is the thing that the robot then needs to learn. But I think there's lots of interesting work out there that other people are working on in order to improve beyond the demonstration, using some kind of human feedback on how well the robot is performing.
Thank you so much.
Hey, thank you very much, Edward, again, for giving this amazing talk, and thanks everyone who attended. I guess that's the end of it. Yeah.
Great. Well, thanks so much for having me. Nice to meet everybody.
It was great. Thank you.